Hello student, now we will see the next concept in the unit 1, algorithmic design strategies. In that we are going to see in this video the first design strategy, divide and conquer. As we have already seen in the previous videos, what is meant by the algorithm? So we have seen algorithm is finite sequence of the instructions that we have to carry to find a solution for a problem. So we have seen that same problem we can solve with the different approaches. So for that different approaches we can write the different algorithms. Some of the approaches are going to deliver much more efficient result. So in the problem solving, devising the good strategies is very much important aspect. In the problem solving, for the efficient solution, we have to use the good strategy for algorithmic design. So if we use the good strategy for algorithmic design, that algorithm will give us more efficient solution for that particular problem. So there are different strategies we can apply to the algorithmic design, that is divide, conquer, greedy approach, dynamic programming, backtracking. In this unit, we will see the first two important approaches, divide and conquer and greedy strategy. In the divide and conquer, we are going to follow the three steps. The first one is, we will divide the problem into the number of the subproblem. So each subproblem is very equivalent to the original problem. In the conquer step, what we will do is, we will solve the subproblem recursively, and after that we will combine the solutions to that subproblem to form the solution of the original problem. So we will see the example so we can understand that how the main problem or the single problem we will divide into the number of subproblem, and after that we will solve each subproblem. So we have to divide this problem until the size of the problem is enough small to solve that problem in a straightforward, and after that what we will do is we will combine the solutions to that particular subproblem to form the original problem. So there are the different problems that we can solve with the divide and conquer. So we will see that the first one is binary search, second one is to find the mean or max from the array, or we can have the quick sort, merge sort. All these are the example of divide and conquer strategies. So next we will see the control abstraction for the divide and conquer strategy. So we can understand this control abstraction, then we can write the algorithm for various problems by using this particular approach. So here first we will see what is meant by the control abstraction. So we have seen that the control abstraction, first we will understand the meaning of the control abstraction. So the control abstraction is nothing but it's a procedure whose flow of control is clear, but whose primary operations are specified by the other procedure whose precise meaning is undefined. So for example over here, so this divide and conquer procedure will have the small p, or it may be SPS function, small function, or it can have the combined function. So through this we can understand the flow of control, but the detailed meaning or precise meaning are undefined. So what we will do is, we will apply the divide and conquer approach to the problem P. Now we will see that whether the problem P is enough small so that we can directly solve by calling the S method. So we will see that small p, this is the function that I will apply on the problem. It's a Boolean function. If it returns the true, means it is a small enough to solve that problem. So we can directly call the S function and to get the solution to this P problem. If small p is going to return false, means we have to divide the problem into the smaller instances P1, P2, P3 like this up to Pk, and apply the divide and conquer to the each subproblem. So in this way we have to apply the divide conquer into the each subproblem, and after that in the second step, that is a combine one, we have to combine the solution to all the subproblem to get the solution to the final problem. So this is a control abstraction. Now we will see what is the computing time that is required for the divide and conquer. So when our problem is enough small to solve the straightforward, so the complexity of that S algorithm is maybe G of n. So, and after that the T of n1, T of n2, in this way up to what the T of nk. So these are the algorithms that these are the time complexity that are required for what the DAC, D and C algorithm for the input size n1, n2, nk. And after that, Fn is a function or the complexity that we required to divide the problem and to combine the solution. We will see detailed analysis further, but this is what the abstract way to represent the computing time of the divide and conquer strategy. Now let's see the first example of divide and conquer strategy, very famous example, that is a binary search. So the name itself is saying that it is a searching problem. So in this particular binary search, we are going to use this particular search algorithm when our list is very large in the size. So we have the large elements, and the next is this element or these elements are arranged in the sorted order. That is the list which in which you want to search the element, it should be sorted. And the third one is we want to search the element in very few comparison. So this is the properties of what the binary search. For example, I will explain first about the linear search so you can understand the difference between the linear and the binary search. Suppose that I have the array, okay. So the array is what the 5, 6, 7, 8, 9, 10. In this way, up to 20 I have the array element. Okay. So suppose I want to search the 19 element within my array. So what I will do, this is what store at a index 0. This is stored at a index 1. So in this way we have all these elements which are stored in the array. So whenever I want to search this 19 one, what I will do, I will first compare my 19 with the 5 because I want to search the 19. If they are not same, I will increment and again I will compare it. So in this way I have to compare linearly with every element until I will reach toward the 19. So in this case, okay, so maybe I am getting what the, or I am doing the 15 what the comparisons total. So when I want to search the same element with the minimum number of the comparison, that time we may use the binary search if my array elements are in the sorted fashion, maybe ascending and descending. First we will see the example with when array is what the ascending. So now we will see how we can implement the binary search. So now consider the 9 elements and this is the array and it has the 0 to 8 indices and the elements are sorted fashion. So now we want to search what the 13. So first we will see the 13, after that we will see some more example, maybe 39. Okay. So now how this particular search algorithm works. So here what we have to do is every time in every step we have to determine the index of the middle element in the list. So here my lower bound is what the 0, my upper bound is 8. So I will do what my low plus end divided by 2, that is 0 plus 8 divided by 2 is 4. So my element is what the, or my mid is going to point toward the 4. So same. So lower bound is over here one of the variable which is initially with the 0. Upper bound is what the initialized to the n minus 1. So n is 9. So 9 minus 1 is 8. And here middle element, what I will do, 0 plus 8 divided by 2. So it will initialize to the 4. Now what we have to do is we have to compare the element which we want to search with what the element which is pointed by this mid. So I will compare the 13 with what, because I want to search 13. So I will compare the 13 with 25. So it is not same means what? The 13 is less than the middle element means what? If this particular element occurs in my array, it should be fall into the first half of my array. So I don't have to search my 13 in my second half of array. So same thing is going to apply. Suppose if I want to compare the 39, so first I will compare with the 25, and if this 39 is greater than the 25, it's not equal to 25, it's greater than, so we have to discard the first half array and we have to search only within what the next half array. So this particular thing that we are going to continue until we are getting what the element, search element. So here, so what we will do now? Now we will re-initialize our lower bound and upper bound with the new values. So what is that? So the lower bound is going to remain same because we have to consider the first half, and the upper bound I will initialize to mid minus 1 or middle element minus 1. So it will initialize to the 3. Again the same step we have to carry. Mid is equal to low plus high divided by 2. So I will get what the 1, and what I will do, I will compare the 13 with the 1. So my element is found. So my algorithm is going to stop and it will return me the location as a 1. Means what? Over here within the two comparisons I am getting the 13. So take the example of the 39 for example. So first time I will compare with the 15 or 25, that is the same step that what we have done. And after that we have seen it is not equal to 25, so we will discard the first half, and what I will do, my lower bound I will initialize over here, my upper bound I will initialize to what the same, it is going to be same. Initially upper bound was over here itself. Here what I will do, I will only re-initialize my lower bound. So right now what is the answer? 5 plus 6, okay, 5 plus 8, okay, and divide by what? The 2. So here 8 plus 5, 13 divided by 2 is nothing but what? The 6. So I will go to the location 6 and I will compare the 39 with this. So I got that element. So within the two comparison I am getting this 39. If I will do this with linear search, I have to compare with the 9, then 13, then 17. In this way, I have to do how many comparisons? Total 7 comparisons. But the same binary for the same list, if I am using the binary search, the same element I am getting within only 2 comparisons. So whenever we want to search the element with the minimum number of the comparison, we can use the binary search. So same thing here. So it is going to be found at this particular index. Now very important, we have to see the algorithm for the binary search. What we have to do. So what is the first step? Array is there, okay, and the element which we want to search is data, and the size of the array is n. So these 3 parameters we have to pass in what the algorithm. These 2 steps are nothing but what? Reading the array element, nothing else. After that we have to enter the element which we want to search. So the element I have entered is what? The data. After that I will initialize my variable low to the 0, that is what? The lower bound, high with what? The n minus 1, that is upper bound. After that I will run this loop until what? This particular loop until what? My low is less than equal to 5. So what I will do in the first step, the mid is what? The low plus high divided by 2, and after that the first step I will do after calculation of mid, I will see that my data which I want to search whether it is equal to a of mid. If it is there, we can write found, return its location, that is return mid, and then we can exit. If that is not case, if it is not equal to the element which is at a mid, so we will see whatever the element we want to search, it is less than a of mid or greater than a of mid. If it is less than a of mid, so we have to re-initialize the high so that we will discard the second half of the array. If data is greater, we have to discard the first, so we have to only re-initialize with the low, and the high is going to be same. So at the low, when I want to consider the first half, I will initialize my half with high with what the mid minus 1. When my data is greater means what, I have to discard the first half, I have to consider only second half, then that time I will initialize only the low with mid plus 1. So I will continue until my low is greater than